If I ask you what is DSP, do you have an answer? After all this time we spent together, what is DSP? What is digital? What is signal? What is processing? It's an open-ended question, right? What is DSP? Digital, we know what is digital, right? To represent numbers using computer, okay? So there will be floating point with integer, that's digital. Quantization, which introduces error, right? So we're talking about analog to digital conversion. So digital is pretty clear. Yeah, the meaning of digital is pretty clear. What's signal? What is signal? Signal is x of n. Okay, signal is x of n. So that's pretty clear too. But then what is processing? That's a part which could be vague. 可能会有点模糊哦。Yeah, what is processing? If I ask you, what do we mean processing a signal? Any idea? 要保证不加分。Any idea? What is processing? All this time we spent together. What is processing? What does it mean to process a signal? All we have learned. What? Filter. Yeah, filtering a signal. For example, we've talked so much about one single thing, right? Low pass filtering, right? That's a kind of processing, very good. What else? Before you started taking this course, what did you expect to learn about processing a signal? Now, this is an open-ended question. So even before we start today's lecture, because this is almost near the end of the semester, okay, so we can just, oh, yeah. What does it mean to process a signal? So you see that signal processing is a pretty vague terminology. I'm not sure, I forgot if I mentioned this to you. Signal has a very broad meaning, right? Anything that can change in time is a signal. Right? This is pretty broad, yeah. Discrete time or continuous time. Signal, but processing is a very vague term. What do you mean to process? The verb. Food processing. What does it mean to process food? That means you have material and you have input, you have output, right? The input might be your raw materials. You might be vegetable, meat, fish, eggs, milk, and what else? Yeah, salt, sugar, everything, right? Food processing, and then after processing, the food becomes something that's ready to be eaten. Okay? That's ready for you to eat. To process something, there's input, there's output. Okay, so filtering is a good example. There's input, there's output. So that's kind of the traditional way of. If you want to ask the question, what does it mean to process something? There must be input, there must be output. Okay, and in the entire course, the input has been signal, but the output is also a signal. For much of our entire semester, the input could be a signal in continuous time. The output could be a signal in discrete time, and we call this a C to D converter. That's one example of processing a signal. Input is a signal, output is also a signal. And then we have input now being x of n, and we use a difference equation with constant coefficient LCCDE, which is a time, linear and time invariant system, right? So the output y is obtained by x convolved with the impulse response. We know that. So that's another example of what it means to process a signal. Input is a signal, the output is also a signal. But now that more and more people in this field, people in the IEEE Society for Signal Processing, when they talk about processing, they have a broader definition. 有一个比较更宽广的定义啊。They have a broader definition. So I'm not showing a video, but just almost 10 years ago, the society, you know IEEE, right? You guys know IEEE? 国际电机电子工程师协会啊 IEEE. IEEE has different societies. One of the societies is called Signal Processing Society. So about 10 years ago, they defined what does it mean to process a signal. They mean more generally, it's also possible that when you process signal, your goal, your purpose is to extract information. So signal processing means to extract information from data all around us. So signal now is generalized to all sorts of data. anything that can be stored can be viewed as signal. Okay, so data is, so more generally to extract information from data, that's kind of a trend. Big data trend, AI trend, you extract information from data around us, not just one-dimensional, but probably two-dimensional images, right? Or three-dimensional video, or any biomedical, any like the data from different domain, okay? So nowadays, signal processing is very much driven toward the notion of information retrieval. You want to extract information or retrieve, 接收截取 retrieve. So nowadays, signal processing is more and more about information retrieval. Information retrieval, did I spell it correct? Retrieve. Is it E-I-O-I-E? Retrieve, to you figure that out. Information retrieval. So in the beginning of the semester, I decided that near the end of the semester, we need to talk about this. Yeah. We need to talk about a few examples, particularly in audio. You'll see, so in this week and next week, we'll start from short-time Fourier transform. So the idea is that if the input is, again, a piece of signal, then after some kind of processing, the output becomes information. And usually, it involves transforming your signal into a different kind of representation, okay? Transformation. And today, we will introduce the short-time Fourier transform. So the one quick summary is that in the end, you'll see that we can transform a one-dimensional signal in time into an image, into a two-dimensional image, where you still use big X to denote the result after transformation. But now we have two variables. The result might be a function of both time and frequency. So that's kind of the general idea, to transform your signal first into a nicer representation and then start extracting information from over there. Yeah. So that's kind of the outline and motivation. So here the short-time Fourier transform, and this handout has been uploaded, so you can take a look. So I was trying to kind of motivate you that we need another kind of Fourier transform. Right. For the entire semester, if I ask you DTFT, what is the definition of DTFT? DTFT is to go from time to frequency domain, right? And the result is a spectrum. It's like a 频谱, right? So we've learned that, the discrete-time Fourier transform. But I claim to you that DTFT is not useful in many applications. It is not. For example, there's one kind of application called query by humming, and kind of a famous company will be, famous app will be SoundHound. Do you know SoundHound? SoundHound is now selling very well, the market. Its stock price has been roaring. It's a company based in the US. And does anybody know SoundHound? Have you heard of? Have you ever felt the need that you go to a restaurant, you heard a song, you like it, but you want to know what song it is? So that's. Do you have this experience? Or do you have an app that helps you do that? Shazam, Shazam is another company. Similar purpose, okay? Shazam example. So to search, to query, to inquire which song it is, there are two possible modes. One is to just turn on your microphone of your phone and then let the microphone record the music, the background music, okay, in the restaurant or in the department store or elsewhere. Okay? But another way is to Yeah, either way. So this means to query the system, ask the system, oh, what is the song? You can also query by humming. Humming 就是哼歌了啊。So if you, yeah, 其实 yeah, somehow it's pretty useful. You can just sing a song into or hum the melody. Just 哼歌啊。Hum the melody. You don't have to be very nice singer. Just sing, and it can at least try to find out what song it is, or what piece of music. By their big database. So that's an example of information retrieval, right? If you think about it. Information retrieval is sing into your phone, which connects to the network, to their server. And in their server, after transformation, you send it to their server and they return information to you. So it's an example, a very good application of signal processing. But I claim that DTFT is not useful. Okay, DTFT is not that useful. And the reason is that, at least in the sound world, sounds are not stationary. Sounds are not stationary. Sound just keep changing its content. That's the main problem. And if you look at the definition of DTFT, DTFT is an infinite sum over time, right? We all know that by now. DTFT is an infinite sum over time. So it goes from time to frequency for sure, but it cannot answer, or it's not convenient for DTFT to tell you if, let's say, if you have a signal in time, and then it goes to the frequency domain. Sure, the result is a spectrum, which has a magnitude and also phase, real part, imaginary part. So you can draw a spectrum, and then maybe you see a major component right here, a smaller component right here, right? And this is in the frequency domain. But DTFT does not tell you, okay, what time does this component occur back in the time domain? So there might be a component at, let's say, corresponding to, let's say, 2000 hertz. Okay, what's an example? You go to a frequency domain, there you can see where the energy is concentrated. But now, just by DTFT, it does not tell you what time this 2000 hertz component occurs back in the time domain. It only tells you that there is 2000 hertz somewhere, but it doesn't tell you exactly where, or it's not convenient. It's not convenient as far as visualization is concerned. Okay, so we need to kind of revise our definition and talk about maybe a version of DTF Fourier transform which involves some kind of a window. Okay, so a new version of Fourier transform, and then we'll tell you that this new version is called short-time Fourier transform. Okay, it's developed. It's based upon DTFT, a new version of Fourier transform, which tells you to transform your signal into a two-dimensional representation. Okay. So another example of signal processing, which just might involve signal that changes all the time. So that's speech coding over the internet. Speech coding. So I have a lecture of like 2 hours just on this very topic, speech coding over the internet. Okay. Nowadays we don't talk. Do you guys talk over your phone nowadays? Do you talk to your friends over the phone? Do you still do that? Do you text more often or talk more often using your phone? Text. Anybody phone? You still talk to, most time you use your phone to talk to people? or do you use any communication software to talk to people? Discord. 还有呢 Yeah, 还有没有 Yeah. Okay, so for just in case you still use your phone to talk to people, sometimes your credit card company give you a call, right? You have to pick up. Otherwise, they lock your credit card. Yeah. I don't have my phone. When you talk to, in case you still talk to people over the phone, let me tell you that actually the speech coding standard has been developed so well. So first of all, the compression rate, data compression rate is like more than 30 times. So there's a high data compression rate. And also, so that means that the voice, when you talk to somebody over the phone, your voice is heard by your friend, and your friend's voice is heard by you, right? But the sound is completely, I should say, completely resynthesized on the phone by streaming. 它是一个语音的串流啊，所以那个 the compression rate is high, so that we don't waste a lot of bandwidth in terms of communication. We want to compress the data first. The compression and then decompress. Okay, so there's the coding, encoding, and decoding, which happens on the fly, on both your phone and your friend's phone when you conduct the conversation. It's amazing. It's amazing. It's been highly developed. Okay, and so you can imagine that first of all, now we can ask the question. We're ready to ask this question. Would you recommend using DTFT as a kind of step for speech encoding? Why or why not? Using this, right? Go to frequency domain. Speech is about sound. Sound has frequencies, right? Do we use DTFT directly, like in this format, using this equation? My answer is probably not. Because like speech streaming, you want to process the speech like right away. You cannot wait until you finish an entire sentence and then hit the release button and then send that sentence, right? It has to happen on the fly in both directions. So therefore, this kind of definition is not helpful. This is like processing a file, maybe. You have a file of 2 minutes. Yeah, then you can define the transform pretty well using this equation. But this equation, I want to give you a feeling, it's not so useful when you have an application like this, when your conversation has to be encoded on the fly in both directions. Now, you hate delay, right? You cannot talk and wait for 1 minute until your voice is delivered to the other end, right? That's not the way we handle such situation, right? So delay is an important factor, okay? So in those kind of applications, when delay is an important factor, we need to seriously think about how to process sound, like using one block using block-wise processing, blocks. You want to process sound in blocks. So that means maybe we process this block first, and then deliver it, encode and deliver it. And then the next block comes in, we process the next block, encode it and delivery, and so on and so forth. Blockwise processing, once you wait for a short time, maybe 20 milliseconds at most, then you process the sound right away to extract information and send it over the wireless network to your friend, to their phone, and so that what happens over there is to decode on the fly. Okay, so you see that to wait until infinity is not a good strategy when delay matters, okay? When processing time matters. You don't want to experience a lag. 不希望有这些的延迟啊。Okay, so another example is automatic transcription of music. All music and speech are, I say to you, are not stationary. They are not like the spectrum can change in time. So I think in the next slide, I do have an example, okay? So this is an example of actually the result of short-time Fourier transform. And on the right, so you see that on the left, this is the result, the two-dimensional representation has a name. We use this terminology spectrogram to call this kind of a representation with time, still left to right, But now the second dimension is frequency. Second dimension is frequency. Is that making sense? I think this makes a lot of sense when you represent music, right? Because otherwise, traditionally, when we think of music, music is something, the sound, vibration that we can hear. And you just study the anatomy, 解剖, the 构造, the anatomy of your hearing organ, the inner ear, and your kind of auditory pathway, 神经的这个连接啊。Fourier transform actually happens along the way. Okay, short-time Fourier transform. So you know that that's why this makes a lot of sense. Musical score, right? What is this domain? This is the time axis, right? Time goes from left to right, and what is this? This is frequency, right? So the Fourier transform, as we'll see in a moment, when we transform our signal into this kind of representation with time and frequency, it actually makes a lot of sense for musical applications. 对于音乐来讲是很 makes a lot of sense. Okay, so for those of you that I need to play this music, but let's switch to, because this is PDF. Okay, we found the corresponding slide in my other course. 你要按好。So let me just show you the music, okay? The settings is this is not my computer. 怎么按放映？好。Okay, yeah. So let me play you this piece of music first. Okay, this is 蓝色狂想曲。Sorry for the loudness. All right, so what do you see? You see that there is一个音阶啊 there's a scale, 音阶啊 scale that goes up, right? And here, what do we see? The traces, right? 有些痕迹嘛啊 So here, the way we read the spectrogram is to look at where, in this example, the dark places. 比较暗的地方啊，比较浓的地方 the dark dense places indicate where the energy is concentrated. Okay, so you see there's trace of a scale going up. Okay. So you can read, yeah, information retrieval, speaking of which, right? So now what are we doing? We have a representation and we start looking at it. So if I don't tell you the score, can you figure out what's going on? That's a task called automatic music transcription, 自动采谱啊 information retrieval. The output now is not another piece of signal but information. Okay? Can you do automatic conversion from the sound first to this two-dimensional spectrogram, then to the score? That becomes an interesting task. It's still not yet 100% solved, okay, up to 2025. So that's another example. So that's a kind of motivation why this kind of transformation and the information retrieval may find applications like such. Okay, thank you for preparing the slides. So let me go back to my PDF. Right, where is the PDF? Can you please? Is it here? How? Okay, so any comments so far? Question? Okay, so today's outline. So what's going on? Tony 未预习结束。So we would okay. So to kind of develop into short-time Fourier transform, we need to first talk about DFT, okay? The discrete Fourier transform. And there is a relation between DFT and DTFT. Then we can mention fast Fourier transform and its inverse. And there's the third topic is finally the short-time Fourier transform. And especially there's a trade-off between time and frequency resolution. Okay? It turns out that when you do that transformation, there is an important factor you need to keep in mind. Okay? That is, what's the size of your pixel right here? Pixels. Two-dimensional representations, right? So now in both frequency and time, we have pixels. So there is a frequency domain resolution. Each pixel may occupy how many hertz, right? Each pixel may occupy how many milliseconds. So there is a trade-off between the time and frequency resolution. You can define by yourself. Okay? So that's a kind of important factor we need to keep in mind when we start using, when we attempt to plot spectrograms. You know what? Actually, I want to jump to C first. I think that's a better flow. Short-time Fourier transform. Okay, so let me just let's jump to the part C first. It's actually easier this way. So now here comes the definition, right? So as I promised, this is the definition of short-time Fourier transform. It's an extended version of DTFT. Now, still summation. So there's a summation over time index n, and the input is your signal x. Okay, the input is signal x, and it involves the usage of a window. And then when you multiply, basically there is a window function, and right here, okay. Surprise if this is the first time you encounter this. Okay, let me finish explaining the equation first. There's a window function. Hahn window, rectangular window, Blackman window, you have learned that. The window function that's applied right here, and then multiply your signal, shift your signal to the left by m samples. Then multiply that result with the window, and the result is a function of n, right? So in the summation, just m is fixed. The summation is over n, okay? So shift your signal to the left by m samples. After that, multiply with the window, and then take the DTFT of the result of the product. Take the DTFT now, the summation index is n, okay? So, and the result becomes, of course, it's a spectrum, but which varies in time, because we are shifting our signal to the left. Okay, so here's a small animation I came up. Okay, I think I do need an animation. Yeah. Let me switch back to the. Yeah, sorry for the inconvenience. My laptop has some problem. It wouldn't charge, so that's why I just out of emergency, I needed my TI to help me. 对到这边，对，这个没有改，前面啊，好，谢谢啊。All right, so now a typical window might look like this. So this, I think this is a Hahn window. Okay, Hahn window with zero, with a finite duration. Okay, finite duration, which lasts from time 0 to about 64. There is a length 64 Hahn window right here, which is used right here. Okay, and so now, so what does it mean to calculate this? Okay, so raised cosine also called Hahn window right here. But now I want to imagine that your signal is this thing right here. Okay, an actual signal, and then for every n, we are going to start shifting it to the left, like that. So there's an amount of shifting to the left. Okay, And at each shift, basically you're fixing the window and let the signal shift. And so when you keep shifting to the left, what does that mean? When you keep shifting the signal to the left, that means we keep looking at later and later part of the signal, right? Because we are looking at the signal through the window. That's the meaning. When they multiply, wherever the window is 0 right there, so that place doesn't matter. All that matters is the part of the signal that's in between right here and right there. So when we shift the signal to the left and further, so each time we shift them, we keep looking at later and later part of the signal through the window by calculating the product, okay? So that's the idea. We keep looking at later part of the signal. That's the idea of short time Fourier transform. Why short time? Short time because this is a short time. Only maybe 64 samples in this example. Looking at the spectrum only in a short time. And that's why we call it short time Fourier transform. It's a kind of Fourier transform which uses only a short time, a duration. So you can focus on later and later part of your signal. So now, as a result, the spectrum is going to change as a function of time because you're looking at later m right here. Is that making sense? Shifting the signal so the spectrum can change in time. They become time-varying spectrum. Okay? So this is the way we come up with the spectral, a two-dimensional representation for a one-dimensional signal. Okay, yeah. So this is like 有一句国语的成语叫做跟这个概念有点像啊，forward 啊 ，forward 白什么过什么，中文系白不对。白驹过隙，什么驹？什么驹？一个马。我写简体字，我要写繁体字啊。然后呢，缝隙的隙，哪个缝隙？有听过这笑话？有听过那个张作霖被炸的笑话 ？Gap， a white horse passing through a gap， 隙怎么写？糟糕。小然后小日小 ，you know what I mean？ 白驹过隙。So this is what I'm saying. What is she? She is the window. Okay. G is the horse. I call this is like a train. Imagine that we are standing. You know, when I grew up, I spent part of my childhood in Banqiao. Anybody from Banqiao right here? Banqiao, thank you. You're from Banqiao. Yeah. I lived in Banqiao, so you know there's 县民大道嘛，台北市叫市民大道。You know why there are such two roads? Because underground you have what? The railroad is underground. 县民大道、市民大道。Have you ever thought about it? 台北市市民大道那个高架桥下面是台铁啊。When I was little, the railroad passes right there. 市民大道还有县民大道。所以我那时候住在板桥的那个埔前国小附近，然后我讲中文啊，那个我以前家里面有亲戚啊，他们家住在对面巷子，对面巷子他们家后面就是铁路，所以一天台铁那主要干点，你知道他火车要经过他家后面多少次，超市啊，然后他们家有个小小的窗户这么小，那后面就是铁轨，火车经过就So that's this. That's a train. So that's a window, literally a window. 真正是一个他们家的窗户。然后我小时候觉得超羡慕他们的，因为我觉得天天都可以看火车啊。我觉得小时候我很羡慕啊。所以 childhood memories, good old time. So see, window, and train. I hope that I help you memorize what's going on right here. We're looking at the train, which passes to the left. So each time, at every moment, we see only one part of the train, which is passing by. And then we analyze that part of your signal. Okay, so that's what it means to take short time Fourier transform. So your spectrum can change in time. Okay. So xm plus m with that shift is like train going to the left. W is a fixed window on the ground, so it's like 白驹过隙，一匹马很快，你只能看到马这样子过去啊，白驹过隙的意思是什么？以管窥天，以离侧海，白驹过隙。啊，意思是我不知道什么意思，我忘记啊。short time Fourier transform. Any question? Any comment? 板桥，你住板桥哪里？哦，比较热闹啊。好。好，我不是很熟，我后来就搬到别的地方去。我在板桥只住了1年多，3岁多的时候，我就印象好深刻，超羡慕那个邻居啊。小时候小孩子真的是很天真的，不会去管说房价或什么的啊，或者环境恶劣，可能那个这些不会，小孩子反而羡慕啊。至少我小时候是这样。好 ，OK, so now is your time. Tell me what signal is this? 有点会不会太看得清楚吗 ？Can you see the figure clearly? Barely. So this is a short time Fourier transform, a kind of signal. Okay, so in the time domain, we have a sequence of pulses: 1, 2, 3, 4, 5, 6, 7, 8, maybe 1, 2, 5, 10, or 12. Yeah, something like that. And fast ones, so the entire time duration is like 1 second right here, and the second, third second, a 3-second long signal with almost 20 pulses of sound. So that's in the time domain, right? So in this example, the time domain, sure, it tells you where the pulses are, but it doesn't tell you actually when you go to your short time Fourier transform. You see the pulses now. 1, 2, 3, 4, 5, 6, 7, 8, maybe 9 right here, and another maybe 12, which follows the 9 pulses. But not only do we see the pulses, but also we get more information right here. What do you see? You see that the energy is kind of, I'm not sure if you can see. Can you see this clearly? Barely? 有看得到吗？看得清楚吗？ All the pulses have an energy concentration near 2000 hertz. Near 2000 hertz. So this is a 2-dimensional representation of a 1-dimensional signal, okay? So you obtain extra information by adding 1 dimension, right? So you see a sequence of about 20 pulses in 3 seconds with energy, with pitch, with the frequency concentration near around 2000 hertz, okay? Does anyone want to guess what sound this is? What is this sound? What is the sound? Huh? Heavy metal music at 2000 hertz? Good one, no. The answer is no. Any other? 想象一下，其实这为什么我今天没有把这个 PPT 给你们呢？想卖关子，有修过我研究所课一些，不要破梗了啊。在座应该没有人已经修过研究。Anyone want to make a guess? What is a sound like this? 20 pulses in 3 seconds and with a pitch with a frequency of about 2000 hertz. 我今天蛮好奇 ，ask ChatGPT。你说 bird chirping, that's a good one. Yeah, what kind of bird? No, that's a good one though. Close. Yeah. Bird, I would say it's probably not bird. If you say bird. It's hard for me to imagine that bird would chirp so regularly because it's like almost equal spacing. It looks more like a man-made sound than something that can happen naturally. Okay, beeper, close. Yeah, rifle gun. Maybe not, because rifle gun, I wouldn't. The sound is probably broadband. It's loud and broadband. the gun, bullet, the air pressure, it probably will not have a concentrated energy near certain frequencies. Yeah. 啊，松鼠，不是，松鼠可能要练过。OK， 所以这也是跟火车有关的。I mentioned 那个亚东医院，对不对？捷运的啊，今天怎么都有点大声啊？弄小声，再听一次啊。对不起，我再放一次，小声一点，希望能小声一点。So I recorded it at Taipei subway. So yeah, so the take-home message today is that next time you go home or you go to Taipei, you can tell your friend, hey, by the way, this is 2000 hertz. I learned information retrieval using short-time Fourier transform, and you can start the conversation. It's a very nice conversation starter, right? No. It shows you show your friend how nerdy you are. 听起来就很宅啊。In case, yeah. 好 ，yeah. So now here comes the resolution part. Okay, the window. So we can sure use a window, the Hahn window, in that equation. Maybe we need to write down the equation somewhere. Okay, so we write down the equation. The equation is x now become big X is a function of both omega and m, and definition is still summing over all n. But in fact, in practice, we only sum at where w is not 0, right? Summation reads from minus infinity to infinity, but in practice, you only need to sum up those 64 points, right? Because the window duration is finite, okay? Your window duration is, let's say, from 0 to L, okay? Your window duration is finite, so in practice, or let me just say, for the sake of being clear about this, from 0 to L. L is the length of the window, okay? Assume that the window lasts from time 0 to time L, okay? Shift your signal to the left by m samples, and then take the product, take the DTFT. So that's a definition of short-time Fourier transform, okay? So which involves a window. So here comes the issue, okay? The window is Hahn, use Hahn window, but then there's a, you need to choose the length right here. You may choose a long window, also a Hahn window with a really long L prime, long length, or you choose a short window, also Hahn window, right? So it's up to you to define what's the length of your window, even given the type of window, okay? So we have two issues. One issue is the length of window, and the second issue is actually which type of window would you prefer, okay? And in this upcoming homework, you have a chance to work on this. But here is a comparison. Same signal, but using different length of Hahn, okay? 1024 versus 4096, okay? 4 times longer. So when the window length is long, and you're looking at your signal now shifted to the left, your signal shifted to the left, so the effect of using long window is pretty simple. Just you're looking at more points at a time. You're summing over from 0 to a long L prime, for sure. So you're taking in a block of signal, a long block of signal, every time you evaluate the spectrum. That's the meaning. That's the meaning, okay? So that, but the downside of that is probably the onset is not so clear. Yeah. The time domain resolution now is lowered because at every moment we use a long window, right? So when the window is too long, then you lose the capability of finding the beginning of your signal, beginning of every with high accuracy. You lose the precision in time. What you lose is precision in time because you're taking in a long block. Okay. For example, if your signal, let's say if your signal is what we just saw, if your signal is just one beep, signal is short but your window is long, and the signal is shifting to the left, right? So in your two-dimensional representation, you'll start seeing something, and in your plot, you see that your spectrum, you see a long area. You see long areas, losing precision in time. You cannot exactly tell what's the beginning time of your signal. I'm not explaining this really well right here. Anyway, so the idea is a long window, you lose precision in time. The signal is shifting to the left, and even though the signal can be short, but if you choose a window that's too long, it becomes hard for you to tell when does the signal start, when does the signal end. Okay, yeah. I don't feel I'm doing a good job right here. What do I have? So I have a remark. When visualizing short-time Fourier transform, we first of all, we rarely talk about the phase. Okay? Everything here, I should clarify, everything we are looking at so far is the absolute value right here. Okay, so we are viewing the spectrogram by plotting the absolute value of short-time Fourier transform. That's the usual way we do it. Okay, we often discard the phase. So that's just the convention. Okay, now can we agree on that? When we visualize the short-time Fourier transform, we often discard the phase. Second note that time and frequency resolution depends on the choice of window. Okay? The choice of window. So I say that long window leads to loss of precision in time. Long window, loss of precision in time. 在时间上面就没办法看那么准了。讲白这意思啊。Loss of precision in time. But what you gain is frequency resolution. When we have more points right here, turns out that computationally we don't calculate continuous spectrum. Computationally, we will see a moment that we actually calculate is the discrete version of the spectrum using DTFT. Okay, so yeah, when you have a long window, the take-home message we'll explain in a moment. When you use a long window, you apply fast Fourier transform. So in the frequency domain, the number of points in the frequency equals to the number of the points in time. It's a like one-to-one linear transformation. Okay, so when you have 4,000 points in time for every block, then in the frequency domain, we are looking at 4,000 different frequencies in the frequency domain. So you gain resolution in frequency. You can have higher precision in frequency, but with a sacrifice of time precision being low. So there's a trade-off between time resolution and frequency resolution when you use a longer window. Okay, more points and more points after transformation, the frequency becomes discrete also. Okay, we'll address this issue right here. Okay, usually computationally, you can imagine that you cannot compute every frequency. We need to discretize frequency. So that's what we are going to discuss maybe for the next hour. We'll talk about a discrete version of Fourier transform. That's exactly by the name of DFT, discrete Fourier transform. Okay, so but that's one example. The next example is again, let me lower the volume first. Now I know I need to do this. Lowest, even lower. Let's try this. So now information retrieval, right? Okay, yeah. Make sense? This is what I'm saying. Short window versus a longer window, okay? What do we see right here? Same signal, but same type of window, same signal, but different length of window. We're taking in 1024 samples at a time. That's the length of window. So as a result, you see like these lines, right? The line right here becomes thinner in the frequency domain. This is more blurry. 这边比较模糊嘛, So that's what I mean losing frequency resolution by going for a short window. But the benefit of doing this is that I argue that the onset, the transition from ba to da, this transition right here is more and more precise, near the boundary of two notes. 两个音符之间的这个 transition, okay? The transition between one note from one note to the next is sharper. You have sharper resolution in time, but here it's not that clear. Clearly in here you have a better resolution in frequency. So that's the difference I want to bring in right here. Same signal, but same kind of window, but by changing the length of window, you obtain a different plot. Okay, so this is something you can choose. You can choose when plotting short time Fourier transform. Okay, so let's take a break. Short time Fourier transform is useful for sound for retrieving information from sound, because sounds are time varying spectra as we hear them. I argue what you hear when you hear sound, you hear them in as time varying spectra, 会随时间而变的频谱. That's one kind of key message I want to deliver today. Spectra now under this definition can change. A spectrum can change in time. Right? So let's take a break and